All right. We'll talk about the basics of nuclear chemistry. Okay? So there's three fundamental particles. We've talked about some. The first one is the alpha particle. The second one is the beta particle, and the third one is the gamma particle. Okay? And instead of calling these particles, I'm going to call them by what they are. It's the type of decay that they go through. So alpha decay, beta decay, and gamma decay. Right? And anything something decays, essentially it's losing parts of itself and it's breaking apart. Okay? So in a decay, in an alpha decay, what happens is that the nucleus is going to end up ejecting a smaller nucleus and making a smaller version of itself. And this thing, the smaller nucleus over here, is an alpha particle. And it's better known as the helium nucleus. So we represent this by writing He here and putting 4 and 2. The 4 represents the atomic mass. Okay, and 2 represents the atomic number. All right? And remember, atomic number defines number of protons and electrons, but in this case, when it's ejected, the helium is missing its electrons. So in atomic chemistry, we generally don't put these here, but you want to think that this thing doesn't have any electrons. So in this case, it's got a 2+ charge from the nucleus. All right? So whenever I go through a type of alpha decay, I am going to be losing a alpha particle. And to give you an example, let me pull up, say, uranium-237. Okay, so here's uranium-237. Atomic number is 92. If we represent this type of equation as an arrow, okay, and you're going to have the alpha particle, helium with a 4 and a 2, okay, that's alpha. And what's going to be left over? Well, according to the laws of thermodynamics, energy cannot be created or destroyed. Therefore, matter cannot be created or destroyed. It can be transmuted into energy, and energy can be converted into matter, but it can't be destroyed. So, since we're just going through a helium or an alpha decay, I've got to balance the mass on each side. So if this is 237 on this side, the other side has to add up to 237. So that means I've got 233 here. Same with the atomic number. Okay? That means I do a 90 on this side. So the element that I'm going to be left off with is thorium. So this is thorium-233. Okay? When this goes through alpha decay. Okay? So that's how alpha decay works. In general, whenever I deal with something that's an alpha particle, the magic number is that once I get to lead, if anything is above lead, it can go through alpha decay. If it's below lead, in general, it doesn't go through alpha decay. Okay? So above lead, we're going to have alpha decay. All right? So anything above lead will be able to go through alpha decay. For beta decay, we have a nucleus, and what gets ejected from the nucleus at this point is an electron. Okay, so the electron gets ejected. An electron is also known as a beta particle. So a beta particle electron gets ejected from the nucleus. And what this is going to do is that this is going to change what the overall nucleus is. If I look at carbon-14, okay, what ends up getting ejected is an electron from a proton. Okay? So you have a proton here, or excuse me, a neutron, not a proton. A neutron ends up shooting out an electron. Okay? When it loses that negative charge, what's going to be left out from the neutron is the mass will remain almost the same, and what you're going to be left with is a neutron that now has a positive charge, or a proton, right? Okay, so when carbon ejects, the beta particle, we represent it by writing electron there. Okay? Electron has a negative charge, but we don't write the negative up in the upper right-hand corner. Instead, we write that it has 0 mass and a -1 charge. So what's going to be left over? Well, whatever we've got is going to weigh 14, because 14 plus 0 has to equal 14. And what plus -1, or what minus 1, is going to be equal to 6. I hope you can do that in your head. 7, you're right. Okay, so what's 7? If you look at your periodic table, nitrogen. So when carbon-14 goes through beta decay, you're left with nitrogen. Okay, so that's a beta particle right there. Gamma decay is another type of decay as well, but in this case, my nucleus is simply energetic, and what I get out is 2 Greek letters, H nu. Now if you're wondering, what is H nu? I don't know what that means. You're going to learn. Okay, H nu is how scientists represent light. This is Planck's constant times the frequency, and that gives you what light is. Okay, this is light. Okay, when light gets released, if I look at a radioactive system, say I've got technetium-83. Okay, and technetium emits a gamma particle. So if it emits light, what's the mass of light? 0, that's right. And what's the charge of light? 0 again. So it's just emitting energy. So what's going to be left over after this? You have a less energetic technetium. Okay? So one way that this is represented is sometimes people write a star here for technetium, which means that it's going in an energetic state. And at the end of the energetic state, it's lost an electron, so it's not as energized as it was. Okay? The important thing to know about these particles is if you look at them, all 3 have their own specific characteristics. All right? Alpha particles, only above lead, okay? And they're heavy, they're massive. They don't have great penetrating power. If you're in a room with something that's emitting alpha particles, odds are you're going to be okay because it's probably not going to penetrate your clothing. If it does, it's not going to penetrate your skin. If it does penetrate your skin, it's in a very small amount. So alpha particles are really not that dangerous, okay, as far as they go. That being said, don't hang around alpha emitters because things that emit alpha generally emit beta and gamma as well in varying extent, depending upon what they are, okay? A lot of them emit gamma, and gamma is bad, and I'll show you why, okay? So because this is so large, it's kind of massive, it's coming out, it's not moving as fast relatively compared to everything else. And it hits the surface, and because it's so large, it doesn't penetrate very well. Remember what happened to the gold. It would get deflected, right? Okay. So the best way to deflect alpha particles is to have something blocking it, like a piece of metal, okay? Well, a piece of metal, a piece of plastic, something dense is good, because dense is going to have more mass, more area. Things are going to hit that and bounce off more likely. That's why X-rays, we want you to wear lead clothing, because density helps deflect radiation. Okay? Beta decay, okay? In this case, it's emitting an electron. It's a lot smaller. And these electrons, when they go out and they hit things, free electrons tend, or what we call radicals, tend to mess things up. Okay? So free electrons are generally bad, and they have deeper penetrating power. And that's a problem for people. Okay? Because as far as people goes, we've got this area right here that's not protected by our dense bones. Radiation comes in, hits these areas, it's going to mess up any organs that are in here. Remember, organs are very important. What important organs do you have here? You've got a stomach, you've got a liver, you've got your kidneys, okay? You've got your entire GI tract is down here. All of these things are going to be bombarded by radiation if you're in the presence of a highly radioactive source, okay? They don't have as much protection. The bone provides protection against radiation sources. Okay? So beta particles have a greater penetrating power, and they're more dangerous. Whereas the most dangerous are things that penetrate the most. Highly energetic light. Highly energetic light likes to do things like get into your cells, change water into a hydrogen peroxide, and then that attacks the DNA and messes up the cells. Usually it kills them. Sometimes it causes burns. There's a bunch of other things. Gamma radiation is very dangerous. Okay? So a gamma emitting source is something you don't want to be exposed to for a very long amount of time. Okay? Also note that because of the type of decay that this goes through, because it's emitting gamma radiation, there's no way for it to really stabilize. It's trying to stabilize by shedding energy, but it doesn't stabilize that well. So a lot of gamma sources, because they emit this energy, they don't correct the fact that their mass is off or they're radioactive as far as their isotopes go. They don't correct that, they've got issues. Okay? The best way for these things to correct to get to a more stable isotope is go through this type of decay. One thing I did want to mention about beta decay, actually a couple of things about beta decay. Beta decay can happen above and below the lead barrier. Okay? So anything that's below lead is going to go through beta decay. Anything that's above lead goes through alpha and beta decay. And anything on the periodic table that's radioactive can emit gamma radiation. Okay? One more fun type thing, if you're a fan of Star Trek, a type of beta decay is the emission of anti-electrons, also known as the positron. Positrons, if you've ever heard of PET, positron emission tomography, okay, the PET scan. This type of scanning uses positrons to label and identify different types of cancers in people. My mother had a PET scan for lung cancer, okay? And the positron emission uses radioactive elements that instead of emitting electrons, emit positrons. Positrons hit an electron, they annihilate, or release a lot of gamma radiation, so they're easy to spot. Things glow hot because of positrons. Okay, so it would be just the opposite, but in this case, what I have is a 0 and a +1 electron in this case. So if I went through positron emission at this point, remember a neutron is emitting a proton at that point, so actually a positron will be emitting a proton, so just said a positron will be emitting a proton. No. Proton emits the positron, E+, and what you're going to be left with is a neutron at that point. Okay? So the overall charge here would be 5, so that means I'd have a very, very heavy boron, because one of my protons would turn into a neutron at that point. Okay? So that's a positron emission. There's other types of radioactive decay and other types of radioactive fun that you can have. That's covered later in the chapter if we get to it. But it's fun stuff. It's used a lot in medicine, which is why you need to know at least something about how this decay goes through. And I just realized I didn't define this, so I'll define it right now. If you've got isotopes are all the same atomic number, but they have different mass numbers. So carbon 14, carbon 13, and carbon 12, all of these are types of carbons. They just weigh a little bit differently, okay? So if you've got these things with different masses, but the same number of protons, you just have differing neutrons. The differing neutrons means that these things are isotopes. So all three of these things are isotopes of each other because they have differing number of neutrons. When neutrons vary from the periodic table accepted values, okay, the normal values, like carbon is 12, when you start branching away from that central number, generally radioactivity is going to increase as well.